So I've got this little Omron motor. It's much like a Panasonic motor. Um, it's using an absolute A with 23 bits of single turn. I've downshifted it by 4 bits to get 19 bits of single turn, which is fine. Just like the Panasonic, you never have more counts than you need unless you need them. Then we can undownshift it. That's no problem. And multi-turn, it said 16-bit. Brushless motor. We've got some connectors for power and feedback. We'll take a look at the data sheet for the motor. Here's the multi-turn information. Multi-turn. There, 16, yeah, so 23 bits of single turn. I'm downshifting it to 19 so I can go wicked fast. And 16 bits of multi-turn. And then we'll take a look for the data for the motor. So knock off the R88M and the Woodruff key and the dash, and you're left with the part number there. 22 occurrences of the motor. So we're looking for the motor specification. Here you go. So this is the winding. It says 100 watts, 0.3 Newton meters of rated torque, 0.95 Newton meters of peak. There's a Newton meters per amp. It's in RMS. We convert that to peak. We'll put that in as data. I measured the resistance. It was 6 ohms. And we know the electrical time constant is 0.48 times that. So tau equals L over R. So L equals tau times R. So 0.8 times the winding resistance that we measured. The back EMF equals the torque constant. So we entered that. Yeah, looks like you need 100 volts AC. But I'm running it with 75 volts. And I'm hitting the rated speed here of 3,000. Theoretically, I could go 6,000. Maybe I can't go that fast with 75 volts. I'm using a ExcelNet. This is maybe designed for a Zenith. But we save a little bit money. It's a small current, 1.5 amps RMS multiplied by the square root of 2 for Copley, from motor to Copley. Motor is RMS, Copley is amps peak. And there's a 4.7 amps RMS. We'll take a look at the wiring for the feedback, general resources, manuals. There's absolute and serial encoder guide. I looked up the absolute A type. All the Japanese are the same, except for everybody's a little bit different. So Panasonic is not like Tamagawa, is not like Harmonic Drive, is not like Nikon A, is not like, whoever, but they're all absolute A. So you wire S and S naught and 0 to 5 volts. In this case, this is batteryless, so you don't need the battery. So it uses the Wiegand effect. I like to give tribute to Dr. Wiegand. So clocking is bidirectional communication. Some people call it RS420, 422, but the drive asks the encoder for position and it replies, and it gives its absolute position from the time of power up, which is multiple turns. So normally when I hook up my system, I just go to one end, spin the motor to 0, and then attach it mechanically. I don't need any fancy homing routine, but we do have those too. So we're going to take a look now at the wiring. There was a little bit of information about the motor side, frame ground, +5 in ground, S and S naught. When I opened up the cable, I got color surprise. So don't pay attention to the colors because every cable is going to be different if you don't have a standard. Anyways, this pin is shield. It's connected to the case of the motor. Not a good idea, but some people do that. As long as you ground the case of the motor to earth and give a nice solid path for the electrons, they won't jam into your feedback and give you CRC faults. I wouldn't do that, but hey, they haven't gone out of business yet, so okay. I flipped it over. I saw pin 1, that's the shield. Pin 3, was 0 volts, pin 4 was S0, pin 7 was S plus, and pin 6 was plus 5 volts. So that's the information for decoding from the little bit that we got there that was accurate. So we're going to go through the basic setup. Brushless rotary, that's a A format, Japanese style encoder, 23-bit single turn. Notice I knocked off 4 bits, so I'm down to 524288 counts per rev, or 19 bits counts per rev, which is more, any more than that, and it's just a bunch of noise or bits. So, you know, what's the point? Okay, I get it. If you're tracking satellites and stuff and you're going slow, you might want it. So you can undo that. Just, you can't go over like 700 RPM with 23 bits unless we do some sort of floating point thing. But just keep it simple. Knock off 4, 16 bits multi-turn. So you can turn it 65536 extra times and it remembers. I chose 4 megabit. Seems to work. New encoder, probably not slow, probably fast, and there will not be a battery error because there is no battery, which is kind of cool. Don't ignore your feedback device. If you get CRC faults, fix your cabling. Maybe don't connect the shield to the motor case. Just my opinion, though. I could be wrong. If you have a break, you can come to a stop. Position, EtherCAT, emulated output. Be careful how many counts per rev. You can divide it down if you want. And then I got the data for the motor. It's a 10-pole motor. And the rest of this stuff came right from this, the data sheet there. It was Newton meters per amps RMS and volts per radians per second in the same units. So you can see it's 17.7 volts per kRPM, 6 ohms measured, multiplied by 0.48 because that's the electrical time constant, 5 millihenries. I hit calculate, got initial tuning values for the current loop. I got 1.2 kilohertz. We could double check these, but this is continuous. Magnitude of the vector, not RMS, so that's good. I set the velocity limit. I entered 6,000. It calculated 3,000 for safety, but I want to go 3,000, so this must be higher than that. I tuned the velocity loop and made some position loop moves. I left the gains for large inertia, but let's take a quick peek to see what the a move looks like. So I did an absolute move to 0. I could do relative 5242880. This will be a 10 rev move. I'm going to monitor the command, the following error, the actual current, the bus voltage, 75 volts, and the back EMF per 1,000 RPM. So maybe I got 17, 8 to 20 times 3, 60 volts. I should go a little bit further, do 10 revs, 100 revs. So we'll get up to 3,000 RPM. And I got a little unregulated supply droop there. My voltage is sitting at not even 60, so I could go faster. Maybe I could go 4,000 RPM. Whoa. Yeah, I got to be careful of that. Let's set this to at least 10% greater than anything I'm going to command. Yeah. We'll see. We seem to be hitting it, though. Oh, yeah, so, okay, you can't go that fast with 75 volts. Following error goes to the moon at that speed. We'll go a little bit faster. Go to the control. Save that to flash. Go to the control panel. Following error fault. Clear the error. Run it again. So, oh, you still can't go that fast either. Interesting. Clear the fault. Try it again. Yeah, the voltage limiting, we're hitting the voltage limit there. Let's just trace that. Miscellaneous, no, event status warning, voltage limited. Okay, so no voltage limit in this case. Try to go a little bit faster. Any voltage limit? So 10% faster. No, no voltage limit. 400. So just checking out the margin here. So the bus voltage droops a little bit. The back EMF goes up. I don't see a problem yet. Ah, there it goes. So let's see what happened right before we get the following error. Yeah, bus voltage limited. So Can't go that fast with this power supply. I got a 75-volt supply. But if you had a Zenus, rectified 120, this is a 100-volt AC motor, no problemo. You can go wicked fast, clear the faults. Yeah, if I load it down, I'm going to get some IR drop, so be careful there. Yeah, it's sort of bumping my head on there. Notice the winding resistance is 3 ohms, so 3 ohms times a couple of amps, and now you're talking, can't go that fast. So 100-volt AC is probably good. The other thing I did, besides getting the data for the motor, is I did some manual phasing, and I decided that this is no load. I'm rotating my current vector. I'm looking at the motor shaft. I like clockwise. I check this box. I see that my my encoder was counting the other way. I check this box, and I had a wicked lag by about 60 degrees, so I put in minus 60. And now I'm the red indicator is following the black needle as I rotate forward and reverse. And let's check out the absolute position after a reset. Boy, I'm really far away from my home. How am I going to get back to home? So we'll reset the drive. We'll make sure, we can unplug the power from the feedback, make sure the batteryless feature is working. Yeah, I'm really far. That's on power up, that's the position absolute from, where the motor was originally. But I'm just going to dial in 0 here and say make the move. Oh, too fast. 300, clear fault, make the move. Okay, so this is just spinning me back down. I turned hundreds of times from the original factory 0 position, and now I'm just going back to the factory 0 position. This will be the 0 position from which when you power up, it'll give you 0. If you're, thousands of turns away from 0, it'll give you a big number. I like to spin it to 0, move my system down to 0, hook up the motor shaft, and it just powers up at the 0 position. That's my calibration. There's also a homing method for absolute immediate home. So you go to some position, like, I don't know, to a limit switch, and then you see what the value is, and then you take the negative of it, and then you do absolute immediate home. But, just go to 0 if that's the home position, and you just spin the motor, hook it up, and go to 0. If you need precision, then that makes a lot of sense, but there's a calibration routine. Okay, that's the Omron motor, easy peasy. Thanks for watching.